class we will discuss about force due to magnetic field. We have already discussed this topic, but today we will derive an equation of force in terms of current. Okay, we will discuss force in terms of current. So over here, this cross over here is the magnetic field. So I have already told you that if it is a cross, magnetic field is directed inward. If there is a dot, it is outward. So magnetic field is directed inward. We place a conductor over here. The length of the conductor is L. Area of cross section is A. So current I is flowing from higher potential to lower potential. And electrons, we know that electrons doesn't flow in the direction of current, it flows opposite to the direction of current. So this is the direction of electron. So electron flows with velocity, that is drift velocity Vd. So I'll note it down. First of all, Vd is drift velocity. So now we'll derive the equation of force. We know that force is equals to Q V cross B. Okay, Q is equals to V cross B. Now Q is the charge or the charge which is moving around. So the charge which is moving over here is electron. So your Q is actually electron. V is the velocity of the electron. So velocity of the electron is Vt, that is drift velocity. So we can replace V by Vt. So we'll just replace it over here. And what we know is, over here the direction of the magnetic field is inward. Okay, the direction of the magnetic field is inward, whereas the direction of the electron is like this. So these two directions are perpendicular to each other. So we can consider theta to be 90 degree. So sine 90 degree will be 1. I am writing this because when we remove this cross product, we can write sine theta. So now in place of Q, that is E, V will be Vd. V remains as B. Sine theta is 90 degree, that is 1. So we do not write that. This is the amount of force. This is when the velocity of the electron and magnetic field are perpendicular to each other. Now suppose if they are not perpendicular to each other. If velocity is not perpendicular to B, then what will be our force? We write F dash. This will be E, that is charge of electron, Vt, that is velocity. I write small v, velocity, B sine theta. Your sine theta will be the angle between velocity and B. If it is not 90 degree, then it will have some angle, that is sine theta. This is F dash is the force exerted by one electron. Okay, it is the force on one electron. This is equation for force for single electron. But we know that inside the conductor there are many number of electrons. So first of all, let us calculate how many number of electrons it might have. Suppose we consider n, small n, that is number of electrons per unit length. Okay, small n is number of electrons per unit length. Capital N is total number of electrons. So total number of electron becomes number of electron per unit length multiplied by length of the conductor and the area of cross section. So this will be the total number of electron present inside the conductor. Now ultimately we can calculate the force, that is the total force exerted by the magnetic field on this charge. So total force F is equals to force on the single charge, that is F dash, force on the single charge multiplied by total number of electrons. So this will give you the total force. Force on the single charge is E Vd B sine theta cross. Number of electrons will be N L E. So now just rearrange this equation. We can write it this way, that is NE BL sine theta. We're just rearranging this. Now, this part. If you remember the equation of drift velocity, from there was a relation between current and the drift velocity. So current is equals to NEVDA. This is the amount of current. You can refer to that chapter also. So this is your current, that is I BL sine theta. You can write it like this. So ultimately that is the equation of force due to magnetic field, and the equation is in terms of current. Now, in place of sine theta, what we can write is, we can write F is equals to I P cross M. This is also what we can write, okay, in place of sine theta. Or, now let us discuss about what happens to the force when there is different angle. Now we know that it is sine theta. Sine becomes maximum, theta becomes maximum when it is 90 degrees. 90 degree means theta is the angle between, theta is actually the angle between magnetic field B and length of the conductor. Okay, it is the angle between magnetic field and length of the conductor. Now suppose magnetic field is in this direction, then the conductor has to be placed perpendicular to each other, perpendicular to this magnetic field in order to get the maximum force. So when theta is 90 degree, force will be maximum because sine 90 is 1, that is maximum value of sine. Now at what value the theta will be 0? It will be 0 when theta is 0 degree. So when it is 0 degree, either when it is parallel. So when the magnetic field and the conductor, if they are placed parallel to each other, then the force due to magnetic field will not be felt or experienced by the conductor. It will be 0 because it is parallel to each other, and when parallel, theta becomes 0 and sine 0 is 0. So when theta is 0, force becomes minimum. So sometimes we don't know the direction of magnetic field, but if you want to know the direction of magnetic field, then what we can do is we can bring a conductor nearby the magnetic field and place it in different forms like parallel or perpendicular. If it experiences a force, then there is some value of theta. When the force is maximum, it is perpendicular. When the force is minimum, it is parallel. So this way we can find the direction of magnetic field as well. So this will be the equation of force in terms of current. And when force is maximum, we can write this one. Okay. So now after this we'll discuss about this is for the force due to a single conductor, single current carrying conductor. Now suppose if in place of one there is two current carrying conductor which is parallel to each other. At that point what happens to the force? We'll discuss that now. We'll discuss about force between two parallel current carrying conductor. Now these are two wires. The current is flowing in the same direction. I1 and I2 is flowing in the same direction. So the force will be towards each other. So this will be the image after that. So suppose if they are in the opposite direction, current flowing in opposite direction, so force will be also in opposite direction. So this will be the image of the wire. So if it is in the same direction, it will attract. If it is in opposite direction, it will repel. So now we'll just find the equation of force due to the parallel current carrying conductor. For that, what we'll do is we'll take two sections of the wire. First is one wire PQ, another wire RS. So in the first one, over here, current I1 is flowing. So current I1 is flowing in this wire. So let us find the direction of the magnetic field in this one. Now, the direction of the magnetic field I1, we can determine the direction of the magnetic field using thumb rule. So if you apply right hand thumb rule, then the direction of the magnetic field will be like this. Okay, like this. So it will be a dot. The direction of the magnetic field will be inward. wire, then the magnetic field will be in this direction. So magnetic field B1 will be in this direction, that is due to current I1. So I write it down. First, B1, that is magnetic field on RS. Okay, magnetic field on RS due to I1. This is magnetic field due to I1. Wherever there is current, there will be magnetic field. So I1 in PQ. I1 is flowing in PQ. So the direction of the magnetic field will be like this. It will be circular, it will not be a straight, but at this point it will be like this, directed this side. So the value of the magnetic field B1 is equals to, we have already derived this one. Magnetic field due to a straight current carrying wire will be mu naught by 2 pi multiplied by I1 by R. R is the distance between point where the magnetic field is there and from where the magnetic field is being generated. That is the distance, okay? Not the radius. Please remember, this is the distance. This is the first one. Now the second thing. This is a magnetic field. Now force. Force on RS. This is the magnetic field. Now the force on RS due to B1. What will be the amount of force and where will be the direction of force? For that we will use Fleming's left-hand rule. So by using Fleming's left-hand rule, this middle finger will give you the direction of the current, index finger magnetic field, and thumb will give you the direction of the force. So current is flowing in this direction, that is I2 is flowing in this direction. So if you consider I2 flowing in this direction, magnetic field in this direction, then what happens? Your force will be in this direction. Okay, force will be inward. So this is by using Fleming's left-hand rule. Remember that. Now what will be the amount of current? F is equals to, we have another equation of current, that is IBL sin theta. IBL sin theta. Now current, which current we are assuming? We are assuming current, that is I2. So current is I2. Magnetic field, which magnetic field we are considering? That is B1. And sin theta. IBL sin theta, sorry, L is the length of the conductor. Alright, let me write capital L. In place of B1, we'll write this value. Okay, B1 will put this over here. I2 mu naught by 2 pi IL by R L sin theta. Sin theta will consider over here to be 90 degrees because sin theta is the angle between B and L. Over here, B and L, length of the conductor, is perpendicular to each other, so this is 90 degrees. So we can consider this to be 90 degrees, so this we can remove. So we can rewrite this. So mu naught by 2 pi I1 I2 divided by 2 pi R into L. F is equals to this. Now suppose we want to remove this L and bring it, this side will come over here. Now, next thing is we consider I1 is equals to I2, which is I. So if we consider I1 and I2 to be same, the value of the current to be same, and if it is I, then we can replace like over here. F by L becomes mu naught by 2 pi. If it is I into I will be I square divided by R. So this is what we get. The force per unit length is equals to mu naught by 2 pi I square by R. Now by using Fleming's left-hand rule, force on PQ by RS, okay, force on PQ by RS will also be towards PQ. The force will be like this. The force due to this will also be like this. This I have already discussed. If there are current is moving in the same direction, force will be towards each other. So this is the amount of force. Now from here we can also define the current. Now the current or the ampere has been derived from defined from this equation. Now suppose we consider R to be 1 meter. Distance between two conductors, okay, to be 1 meter. And this force per length will be 2 into 10 to the power minus 7 Newton Newton per meter. Okay, if this is the force per length, then current will be 1 ampere. So if force per unit length is this, where R is 1 meter, then your current will be 1 ampere. From that, we can also find the value of mu naught. We'll just do that. Now, force per length is 2 into 10 to the power minus 7 is equals to mu naught by 2 pi. Current is 1 ampere, 1 into 1 is 1, R is also 1. So from here, your mu naught becomes 2 pi into 2 into 10 to the power minus 7. So this becomes 4 pi into 10 to the power minus 7. This is the value of mu naught. The unit of mu naught will be Newton per ampere square. So from here, the value of mu naught can be derived, and even the ampere can also be defined by this equation that is given in the book. You can refer to your book. So with this, we have come to an end to this chapter. If you have any numericals or any doubt, please tell me in advance so that in the next class I can correct all those things, and even I can help you out with the numericals. So this much for today. We'll continue in the next class. Thank you.